Hello, and welcome back. Um, so, obviously not in the middle of having a code, and I didn't do a lot of 2021 videos, but you know what? I sort of had an interest in doing one, and I remembered this problem, day 9 in 2021, that had kind of a cool solution. Not too complicated, but I thought it might be fun to walk through. So that's what we're going to do today. Day 9, 2022. Um, Smoke basin. The idea for part one is you have this big rectangular grid of numbers. 9 is the highest, 0 is the lowest, and the objective for part one is to find the low points. So um, when you think of a point, you basically compare it to the other points in the matrix in the four cardinal directions, north, south, east, west. And if that point is lower than the ones that are adjacent to it, then that's a low point. And the idea is to find all the low points, and then we try and find the sum of the risk levels. And a risk level is 1 plus its height. Fair enough. Okay, so let's look at our input first. We do indeed have a big rectangular grid of numbers. So, like usual, we'll kind of format the input first. So 09.txt. We get the first part, bunch of lines. We can mix those, and then for each execute to get numbers. And what's the size of this? It's 100 by 100, so pretty sizable input. This is our input, which we will assign to P, as is tradition. Okay, now when we think about comparing a value to any of its neighbors, then one of the first things that I'd reach for in APL is the stencil operator. Oh, my cat's here. Once again, another classic. So the stencil operator, let's see, if I take a 3 by 3 matrix of iota 9, looks like that, and then stencil, we can take 3 by 3 slices, and then we can just enclose them to be able to see what the stencil operator is actually doing. And you can see that it moves through each element in the matrix individually and takes this sort of 3 by 3 submatrix. And it feeds that to the function on the left of the operator here. So when we're looking at our input, we just have to use the same configuration for stencil and have a function that looks at the middle of the matrix and compare it to the four values in cardinal directions adjacent to it. Now the problem with stencil, as I said, it goes through every element in the matrix, which means for these corners and for the edges, there aren't sufficient elements to make a 3 by 3 matrix. So it fills it with zeros. And as far as I can tell, and I've been through the documentation and everything, there's not a way to change this fill element. So what we're going to do for our input is we're just going to subtract 10 from all the numbers. And that's going to give us a bunch of negative numbers. But now, when the stencil operator fills in with zeros, a 0 is then guaranteed to be, hang on, a 0 is guaranteed to be higher than any of the other negative numbers in our input here. So when we're comparing values and we're trying to find low points on the edges or the corners are going to be lower than the zeros that the stencil operator fills in. So that's just kind of a way to massage the input to work around that quirk of the stencil operator. So we have P minus 10 and, oh, one other thing that we're going to need. I'll just call this C for coordinates, and we need a way to index into the 3 by 3 matrices that the stencil operator presents us so that we can get those 4 cardinal directions. Now I'm in the default index origin, which is IO1, so we're using 1-based indexing here. So if we think about the top element, that's going to have coordinates of 1, 2. If we think about the leftmost element, that's going to have 2, 1. The rightmost element is going to have 2, 3. And the bottommost element is going to have 3, 2. So those are our coordinates. Okay, so we have p minus 10. This is our massaged input. We're going to take 3 by 3 slices, feed it into the stencil operator, and let's see. So we'll take the middle element of the matrix that's returned. So we're just indexing 2, 2 here. That's the middle element. And then we want to make sure that it is less than the 4 cardinal directions. So we can just index directly into it, into that submatrix that's returned. And then, so this function, less than, if we do this, oh yeah, I just called it C. This function, if we do this, it's going to return us something like this. We now have 100 by 100 by 4. What we really want is to and reduce all of these to make sure that the middle value is lower than all of the cardinal directions. So we do this, and you can see a couple ones hanging around. These are our low points. That's what they signify. The other thing you can do here, instead of an and reduce, put this on the bottom, is you can use the inner product operator, and you can say and dot greater than. And it gives you the same result. Okay, and then if we take iota underbar, we get the coordinates of all of our low points. And we can, because the score calculation here, we need to actually index back into the input and add 1. So we can just say P and long square brackets here to index back in. And then we can just do 1 plus reduce to add up all of those values. Answer is 465, and indeed, that's what we have here. I've been looking for more opportunities to use the inner product operator. Not necessarily because it saves any characters, it does sometimes, but just because I think it's cool. So just like that other one we looked at, we can do plus dot plus here, and that will give us the same result. Okay, so what is part 2? You need to find the largest basins so you know what areas are most important to avoid. Number of locations within the basin, including the low point. Importantly, locations of height 9 do not count as being in any basin, and all other locations will always be part of exactly one basin. And the idea is, we kind of expand out from these low points, and we see the size of all the basins. We calculate the sizes. We take the 3 largest basins and multiply their sizes together. And that gives us our final answer. So if we look at our input and we just say 9 equals, so we're looking at all the locations that are equal to 9. It's a little bit hard to see, but you can sort of see how all these ones are denoting contiguous regions. So when we're expanding out the basin, we don't go diagonally, we go again in the cardinal directions. And each one of these ones, these are 9s in the input, so they're not part of any basin. You can think of them as our boundaries. And our job is essentially to expand out from our low points, identify all of them somehow, and then calculate the sizes of the different basins. The way you might do this in a more classic imperative language is you do a flood fill, basically. Um, so you do a queue, or you do it recursively, and you just have your low points. You expand out from all of them, and you keep track of the different coordinates that are going to be part of each basin. In APL, we could do that, although for this problem, when I did it back in December, I came up with a solution, again using the Stencil Operator, that I thought was pretty cool. So when we think about expanding outwards, well, let's let's mess with our input a little bit, um, so that we get something that's a little easier to solve with. So we have 9 equals p. Let's negate this. This will become apparent why I'm doing this in a minute, but now all of our boundaries are denoted by negative ones instead of ones. And if I come back up here, as part of our part 1 solution, we got all the coordinates of the low points. So if I assign those coordinates to L here, there's our part 1 answer, but now if I use L, these are all the coordinates of all of our low points. So I can say, -9 equals p, so all the 9s are now represented by -1s, and I can use the at operator and say at the low points, I want you to denote each of them with a unique identifier. So iota length L. This basically, well, I can show you. Iota length L is just, it's counting from 1 up to the length of our array of low points, which is it's 211 points. And so we can say -9 equals p at the low points, assign these unique identifiers. And now you can see that we mixed in a few numbers here. So we got 7, we got 17 over here, 24, 195. Basically, each one of our low points has been incorporated into the matrix and has been given a unique identifier. And now when we think about our flood fill, we can operate on this matrix, and we can assign those unique identifiers to all of these zeros that haven't been covered yet. And then at the end, we can use something like the key operator to count the sizes of each one of the basins. So if we were going to use the stencil operator, we'll need a function on the left-hand side. So we're going to put together a function called f. And importantly, remember in our problem description, it says that locations of height 9 do not count as being in any basin. So we want to skip those. Now they're represented by -1 here in our matrix. So we'll just say, we'll index into the middle of the submatrix that the stencil operator gives us. And we'll assign this to m because we might use it later. And we'll say if -1 equals the middle element, meaning that that's the one that we're operating on, don't do anything. Just return -1 again. So when we're using this function, when the stencil operator is looking at submatrices centered on -1s, those are going to remain constant and they won't change. Otherwise, we take the submatrix, we index into those cardinal directions that we had before. We'll concatenate the middle value, and then we'll take the maximum of all of those. So what's going on here? Basically, when we're expanding out from our numbers, we're expanding into zeros. And we'll also have some -1s in the mix, right, when we edge up against them. So if I had a 3 by 3 matrix, let's say centered right here, 0, 0, -1, 0, 0, 0, and then 0, 1, 9, 5, 0. And we're centered right here on this 0 element. We want to look at the cardinal directions and we just pull the maximum value from all of those, and we include the middle so that as the stencil operator goes through, it's not um, it's not overriding those middle values with zeros or anything else. So I think this will make a little more sense if I show you in action. So this is our function f, which will go on the left side of our stencil operator. Here's our matrix with nines replaced with negative ones, and each of our basins having a unique identifier. And if I do 3, 3 stencil operator using f, our function, you can see that in a single iteration, we've now begun to expand outwards from our low points in the cardinal directions. And you can see here, like this 30 was the center point. We've extended down, we've extended left, but where we jut up against the negative ones, those are constant. Those aren't changing. Okay, great. Hopefully that makes sense. Now, we can continue to iterate this function. We can do it multiple times using the power operator. So I could run this, let's say, 2 times instead of just once. And you can see that we've continued to expand out. You know, we now have a bunch of 195s, we have a bunch of 30s. The 30s are, again, going around these negative ones, right? And actually, we can run it more than twice. We can run it until the values don't change anymore. So the stencil operator is running, it's expanding into these zeros, it's expanding out and out, and eventually all of the zeros are going to be covered. And then at that point, you know, the negative ones aren't changing because we set our function up so that those remain constant. And none of the basin numbers are going to be changing because they're going to be the maximum. They're already going to be the maximum of the middle element and everything in the cardinal directions. So we can actually just run this until convergence, which is this power match combo here. This basically says that you keep running the function to the left of the power operator, and if the output of a successive iteration is equal to the output of the previous iteration, then stop and return that output. And if we do this, now you can see that, you know, it terminated, which is always a good sign. But not only that, we've expanded everything out from our low locations, and we should not have any zeros left in this matrix, which we don't. Okay, so what do we do from here? What does our problem actually ask? It says we need to determine the size of a basin, which is the number of locations within the basin, including the low point. And then what we do is we take the 3 largest bases, multiply their sizes together, and that will be our answer. So we have our matrix here. We can put it into a vector using Rabble. And we want to take these negative ones out because remember the negative ones denote 9s in the input, and they don't count in any basin size. So we can just use the without function here. So we're removing negative ones. And we can use the key operator to group these, and we're just interested in the length of each group, like so. And we can sort them in descending order, like this. And then we can do 3 take to get the 3 largest, and we can do a multiply reduce to get our answer, 1269555, which is our answer. Excuse me. Yeah. So I thought this was pretty cool. It's a neat. I use the stencil operator a lot in these advent of code problems. Obviously for a lot of the cellular automata stuff that comes up, but it also surfaces a lot in these rectangular numerical matrix problems that we get each year. So if we were going to look at what this looks like as a finished solution, yep, then we can put this all together in the text editor here, and we'll scroll up. Okay, so this is our, we're just parsing our input here, and we have our cardinal direction coordinates, and then we need the version of part 1 that assigns the coordinates of our low basins. So this is part 1. And then we created a function to go on the left half of the stencil operator for part 2. And the actual part 2 calculation is here. And if we run all of this together, 465, 126, 9555, which are our 2 answers for part 1 and part 2. So this is the complete solution here, which I think is very similar to the one that I posted on the Reddit thread way back in December. So yeah, anyway, I thought it was a cool use of Stencil. Just kind of, I felt like making a video, so and I sort of remembered this problem. Can't promise any more until next year at least, but hopefully this was entertaining and or educational. All right, until next time, thanks for watching.